Imagine gazing up at a night sky filled with countless stars, wondering if somewhere out there, another pair of eyes might be gazing back. Now, imagine that question isn't just philosophical, it's scientific. Because scattered across the silent, endless dark, signals are reaching Earth, strange, powerful, and utterly mysterious transmissions from the deepest corners of space that scientists still struggle to explain. Some last only milliseconds, others repeat, a few seem almost intentional. These aren't just astronomical phenomena, they're cosmic messages in a language we have yet to fully understand. And tonight, we're diving into 25 of the most baffling signals ever detected. From the infamous WOW signal that stunned astronomers back in 1977 to the eerily regular beat of fast radio bursts that arrive like clockwork from galaxies billions of light-years away, each of these signals tells a story. A story of curiosity, of confusion, and of the thrilling possibility that we might not be alone in this universe. Some signals are so powerful, they outshine entire galaxies in mere moments. Others are so precise, they challenge everything we know about physics. And a handful have even sparked serious debate about whether we might finally be hearing the first whispers of an extraterrestrial intelligence. This journey isn't just a countdown, it's an exploration into the very limits of human knowledge and imagination. We'll travel from massive radio telescopes, scanning the heavens, to the profound theories, trying to make sense of these cosmic anomalies. So settle in, open your mind, and get ready to venture into one of astronomy's greatest ongoing mysteries. Whether you're a seasoned space enthusiast or just curious about the universe's hidden wonders, what follows will leave you captivated, questioning, and truly amazed by the strange and stunning signals echoing across the cosmos. Our journey into the cosmos's greatest mysteries begins not with a complex burst of data or a repeating pattern, but with a single, startling event that lasted just 72 seconds. It was August 15, 1977, at the Big Ear Radio Telescope in Ohio. This massive instrument, essentially a giant flat plane that scanned the sky as the Earth rotated, was diligently listening to the heavens as part of the ongoing search for extraterrestrial intelligence, or SETI. A few days later, volunteer researcher Jerry Amon was reviewing the computer printouts, a continuous scroll of paper filled with rows of alphanumeric characters representing signal intensity. As his eyes scanned the data, one particular sequence made him stop dead. He circled it in red pen and, in a moment of pure, unadulterated astonishment, wrote a single word next to it that would echo through history: "Wow." That sequence was 6EQUJ5. To the untrained eye, it looks like a random jumble of letters and numbers, but to an astronomer, it was a lightning bolt from the void. The Big Ear telescope used a specific code where numbers 1 through 9 represented signal strength, and letters from A onward represented intensities from 10 upward. This sequence, 6EQUJ5, translated to a signal that rapidly rose in strength to an unprecedented level, over 30 times the background noise, and then fell away, creating a perfect, narrow peak on the printout. It was a narrowband signal, meaning it was concentrated on one very specific frequency, and that frequency is perhaps the most tantalizing clue of all: 1420.40575 MHz. This is the hydrogen line, a frequency that scientists had long hypothesized would be a logical choice for any advanced civilization attempting to communicate across interstellar space. Hydrogen is the most abundant element in the universe, and a signal broadcast at its natural emission frequency would be easily recognizable as artificial, a universal lighthouse beacon saying, "Here we are." The WOW signal fit this profile perfectly. It wasn't noise. It was a deliberate, powerful shout in the one channel everyone agreed was the cosmic watering hole. Yet, after that brilliant 72-second burst, it was gone, despite decades of repeated, targeted searches by countless telescopes pointed at that exact same patch of sky in the constellation Sagittarius. The signal never returned. Its one-off nature is the core of its enduring mystery. If it was a deliberate transmission, why did it stop? Was it a targeted message that simply missed its mark, sweeping over Earth like a lighthouse beam in the night? Or was it something else entirely? The most prominent natural explanation points to a comet. In 2016, an astronomer proposed that the signal could have been caused by the hydrogen cloud surrounding two known comets that were in that region of the sky at the time. The idea gained some attention, but was ultimately dismantled by the scientific community. Critics pointed out that the comets were not actually in the telescope's field of view at that precise moment, and more importantly, such a hydrogen cloud would emit a broad, diffuse signal, not the intensely powerful, narrowband signal that was observed. The comet theory, while creative, failed to explain the very data that made the WOW signal so extraordinary in the first place. Other theories suggest it could have been an incredibly rare and fleeting astrophysical event that we simply don't yet understand, or even a reflected signal from a piece of human space debris bouncing a transmission from Earth back to us. But each explanation falls short, unable to fully account for its perfect characteristics. The WOW signal remains the white whale of SETI, a solitary, perfect candidate that has never been matched, a ghost in the machine that continues to whisper the thrilling possibility that for one brief moment in 1977, we were not alone. If the WOW signal was a solitary shout in the cosmic dark, then fast radio bursts are the universe's unpredictable, deafening screams, discovered entirely by accident in 2007. These events are among the most energetic and baffling phenomena in all of astronomy. Astronomer Duncan Lorimer and his student David Narkevic were the first to stumble upon one, but they weren't even looking for something new. They were sifting through old archival data from the Parkes Radio Telescope in Australia, recorded back in 2001, searching for new pulsars. Buried in that data, they found something that defied all explanation, a single, colossal burst of radio energy that lasted just 5 milliseconds. In that blink of an eye moment, it released more energy than our sun puts out over 80 years. The scientific community reacted with deep skepticism, and understandably so. The signal was so powerful and so brief that many wondered if it was merely some form of terrestrial interference, a glitch from a microwave oven on the observatory grounds or a passing satellite. But as years passed, more of these bursts were found by other telescopes around the world, confirming that they were not only real, but also originating from far beyond our galaxy. Their immense dispersion, a measure of how the signal's waves are stretched out as they travel through space, placed their origins billions of light-years away from the depths of intergalactic space. This is what makes fast radio bursts so astonishing. For a signal to be detectable across such a vast, mind-boggling distance, its source must be phenomenally powerful. The energy released in those few milliseconds can outshine an entire galaxy of stars. Theorists have scrambled to propose explanations, with ideas ranging from the cataclysmic deaths of massive stars to eruptions from highly magnetized neutron stars called magnetars. Some have even ventured into more speculative territory, considering the possibility of immense alien transmitters or other technological origins. Yet, despite hundreds of detected bursts, no single theory can comfortably explain all their peculiar characteristics, particularly the fact that some of them repeat randomly, while others are one-off events. They are a true cosmic paradox, incredibly common, occurring thousands of times a day across the entire sky, yet emanating from sources that remain completely invisible to us, hidden behind the veil of deep space and time. Just when astronomers thought they had a handle on the chaotic, one-off nature of fast radio bursts, the cosmos delivered a curveball that reshaped the entire field. In 2015, the Arecibo Observatory in Puerto Rico, a colossal dish nestled in a natural limestone sinkhole, detected something unprecedented. A burst designated FRB 121102 flashed across its receivers. This in itself wasn't unusual. By then, several such events had been cataloged. But then it happened again and again. Over subsequent observations, this same source in the constellation Auriga erupted over and over, sometimes in a predictable pattern, other times in frantic, unpredictable clusters. This was no cataclysmic blast signaling a stellar death. This was a source that was very much alive and actively repeating. The immediate implication was profound. The leading theories for one-off bursts involved singular, destructive events, the collision of two ultra-dense neutron stars, or the final, spectacular collapse of a star into a black hole. These are, by their very definition, events you only get to see once. The repeating nature of FRB 121102 completely invalidated those models for this source. Whatever was creating these bursts had to be a persistent engine, something that could survive its own apocalyptic outbursts and reload for another round. This forced a dramatic pivot in scientific thinking, narrowing the field of possible culprits to objects that are both incredibly powerful and remarkably durable. The next great challenge was to find its home. Pinpointing the origin of a millisecond burst of radio waves from billions of light-years away is a monumental task, akin to locating a single specific grain of sand on all the beaches on Earth from an airplane. The breakthrough came from a coordinated global effort using the immense resolving power of the Very Large Array, or VLA, in New Mexico. Unlike a single-dish telescope that sees a large, blurry patch of sky, the VLA is a network of 27 individual radio antennas working in concert as one giant eye. This allowed astronomers to achieve a level of precision previously impossible. After countless hours of observation, patiently waiting for the source to erupt again while the VLA was watching, they succeeded. They narrowed its location down to a tiny, precise point in space. That point was not in the void between galaxies, nor was it in a grand spiral like our own Milky Way. The repeater's home was a small, faint, and unassuming dwarf galaxy, more than 3 billion light-years from Earth. This was another crucial clue. Dwarf galaxies are known to be ancient, metal-poor environments, the kinds of places where the processes of star formation and stellar death can differ from those in larger galaxies. This environment seemed to favor the existence of a specific type of stellar remnant, a magnetar. These are a special class of neutron stars, the collapsed cores of massive stars, but they possess magnetic fields so unimaginably powerful they are quadrillions of times stronger than Earth's. The thinking is that the titanic stresses on a magnetar's crust could generate colossal starquakes, each one cracking open the surface and releasing a blistering torrent of energy we see as a fast radio burst. The repeater's behavior fits this model well, a restless, magnetically tortured object periodically letting off steam. Yet, the mystery only deepens with the signal's properties. Analysis revealed that the bursts from FRB 121102 are highly polarized, meaning their light waves are all oriented in the same direction. Furthermore, they exhibit an effect known as Faraday rotation, where their polarization twists as the signal travels through a strong magnetic field. The degree of twisting observed is extreme, the strongest ever measured from an astrophysical source, and it points directly to the signal having passed through an incredibly powerful and dense magnetized environment, like the region immediately surrounding a magnetar. While this evidence strongly supports the magnetar theory, the door for more exotic explanations, however slim, remains ever so slightly ajar. The precision and repetition have, for some, kept alive the fringe possibility of an artificial origin, a powerful beacon perhaps, though the natural explanations are far more robust and widely accepted. FRB 1211-02 didn't just give us a new mystery, it gave us a laboratory. For the first time, we had a known, persistent address to which we could point the world's telescopes, a gift that keeps on giving, challenging our understanding of the most extreme physics in the universe. In the chaotic symphony of cosmic signals, where randomness often seems to be the only rule, astronomers were stunned to discover a beat, a steady, predictable rhythm emerging from the noise. This brings us to fast radio burst 180916, a signal so hauntingly regular it feels almost engineered, discovered by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. This repeater does something no other cosmic phenomenon had been seen to do before. It keeps a schedule. For approximately 4 days, it actively erupts with bursts. Then, as if a cosmic switch is flipped, it falls completely silent for about 12 days. This entire cycle, from the start of one active period to the next, repeats with clockwork precision every 16.35 days. Identifying this pattern was a monumental feat of persistence and data analysis. It required sifting through months of erratic bursts, searching for a statistical ghost of a pattern hidden within what appeared to be pure chaos. The team had to account for gaps in observation time, as no single telescope can watch one patch of sky continuously and then piece together the puzzle from fragmented data. When the 16-day cycle finally emerged from the numbers, it was a eureka, a moment that sent shockwaves through the astrophysics community. For the first time, we weren't just watching a cosmic object, we were predicting its behavior. This incredible periodicity is a powerful clue, and it points overwhelmingly to one compelling scenario: an orbital dance. The leading theory suggests the source of the bursts, likely a magnetar, is locked in a binary system, circling a companion object. Imagine a lighthouse on a distant planet with a wildly elongated orbit. For a part of its long journey, it faces us, and we see its light. For the rest of its orbit, it's turned away, and we see nothing. In this cosmic model, the companion object could be a massive star or even a black hole. The 12 days of silence could be the period when the source is eclipsed by its companion, its radio waves blocked by the star's thick plasma or the black hole's immense gravity. Alternatively, the cycle might not be about blocking the signal, but enabling it. Perhaps the bursts are triggered by a specific point in the orbit when the magnetar is closest to its companion. The immense gravitational or magnetic stresses could crack its surface and unleash the fury we detect as a fast radio burst. This regularity challenges some of the more cataclysmic one-off burst models, as a colliding system would have a very short lifespan, not a stable multi-year orbit. Conversely, it powerfully strengthens the magnetar model, as these dense stellar remnants are perfectly capable of existing in binary systems and flaring repeatedly. The very existence of such a predictable pattern feels, to some, almost artificial. It's the kind of regularity we might expect from a beacon, a deliberate signal designed to be noticed as non-random. While the natural binary model remains the most scientifically parsimonious explanation, the sheer precision of FRB 180916 continues to captivate and fuel the imagination, serving as a profound reminder that the universe often operates with a hidden order we are only just beginning to perceive. Just when we thought we had the pattern down, that these immense bursts were exclusively visitors from the far reaches of intergalactic space, the universe delivered a stunning surprise from right in our own cosmic backyard. Enter Fast Radio Burst 2020-00120E, a signal that upended expectations by not coming from billions of light-years away, but from a mere 11.7 million light-years. To an astronomer, that's practically next door. The origin point was traced with startling precision to a most unlikely location, a globular cluster orbiting the majestic spiral galaxy Messier 81. This was a profound shock to the scientific community. Globular clusters are ancient, dense spheres of hundreds of thousands of stars, among the oldest structures in a galaxy. They were considered stellar retirement homes, calm, stable, and utterly devoid of the violent, young stellar objects thought necessary to create such explosive phenomena. Finding an FRB engine in such a serene and ancient environment was like finding a Formula One race car parked in a museum. It simply didn't fit the established models. The very location forced an immediate and dramatic re-evaluation of what kind of object could be responsible. The incredible proximity of FRB 2020-00120E was its greatest gift. It transformed the signal from a faint, distant mystery into a nearby laboratory specimen that could be studied in exquisite detail across the entire electromagnetic spectrum. For the first time, astronomers could point not just radio telescopes, but also optical, X-ray, and gamma-ray observatories directly at a known FRB source. This multi-wavelength approach is the key to cracking these cosmic codes, as it allows scientists to see the full picture of the explosion, not just the radio component. And almost immediately, this coordinated effort paid off with a monumental discovery. The source was conclusively identified as a known magnetar, a highly magnetized neutron star designated SGR 1935 plus 2154. This confirmation was the smoking gun the astronomy world had been waiting for. On April 28, 2020, this same magnetar let out a roar that was detected simultaneously as a millisecond radio burst and a bright X-ray burst. This single event provided the strongest evidence yet that at least some fast radio bursts are indeed generated by these incredible cosmic powerhouses. The theory finally had its proof. The unimaginable magnetic fields of a magnetar, trillions of times stronger than Earth's, can snap and reconfigure in a starquake, releasing a cataclysmic pulse of energy that ripples across the universe. Yet, the mystery of fast radio bursts is far from completely solved. The detection of this galactic intruder answers a fundamental what, but opens up a deeper how and why. We now know magnetars can produce FRBs, but the mechanisms that create a relatively weak galactic burst versus an extragalactic blast that can outshine a galaxy are still not fully understood. Furthermore, while this confirms one origin story, it doesn't necessarily explain the bewildering variety of behaviors we see in deep space FRBs. Why do some repeat randomly while others, like the famous WOW signal, are one-off events? Why do some, like FRB 121102, exhibit incredibly strong magnetic signatures, while others do not? The discovery of FRB 2020-00120E is not the end of the story. It's a crucial corner piece in a vast, complex puzzle, proving one source while simultaneously highlighting that the cosmos likely has more than one way to generate these brilliant, fleeting screams across the void. Long before the terms repeater or periodic cycle entered the lexicon of radio astronomy, there was just one, a solitary, unexplained blip that defied all categorization. This is the story of the Lorimer burst, officially designated Fast Radio Burst 010724, the original anomaly that single-handedly opened a new window onto the universe's most violent and secretive phenomena. Its discovery wasn't the result of a targeted search, but a moment of pure serendipity, a testament to the fact that sometimes the greatest discoveries are found not by looking for something specific, but by looking carefully at everything. The year was 2007, and West Virginia University astronomer Duncan Lorimer had given his student, David Narkevic, a seemingly mundane task. They were analyzing archived data from the Parkes Radio Telescope in Australia, recorded 6 years earlier in 2001. The goal was a routine hunt for new pulsars, the spinning neutron stars that emit regular radio pulses. As Narkevic sifted through the reams of data, a pattern emerged, but it was the opposite of what they were seeking. Instead of a steady, repeating beat, he found a single, colossal spike of energy that appeared and vanished all within an astonishing 5 milliseconds. It was a flash of unimaginable power, a transient event of a kind no one had ever formally documented before. The signal's properties were immediately bizarre. Its most telling feature was its dispersion measure, a key metric astronomers used to estimate distance. As radio waves travel through the sparse sea of electrons in interstellar and intergalactic space, higher frequency waves arrive slightly before lower frequency ones, causing the signal to spread out or disperse. The greater the dispersion, the more material the signal has traveled through, and thus, the farther it has come. The dispersion measure for this burst was enormous. It pointed unequivocally to an origin far outside our Milky Way galaxy, placing its source billions of light-years away in the deep intergalactic void. To release a signal that could be detected from such a mind-boggling distance, the source had to have unleashed more energy in 5,000ths of a second than our Sun emits over 80 years. Presented with such an extraordinary claim, the scientific community reacted with profound and understandable skepticism. The principle of extraordinary evidence for extraordinary claims weighed heavily. Critics proposed a laundry list of potential terrestrial explanations. Could it have been a glitch in the telescope's electronics, a burst of interference from a passing satellite or an aircraft? Perhaps it was something even more mundane, like a microwave oven being opened prematurely by a researcher at the remote observatory, a source of radio frequency interference that would later indeed be caught mimicking an FRB at Parkes. For years, the Lorimer burst remained an intriguing but unproven outlier, a celestial ghost that many believed was probably just a terrestrial phantom. Yet Lorimer and a small group of believers persevered. They meticulously ruled out every possible local explanation. The signal's characteristics were all wrong for human-made interference. Its frequency sweep was too perfect, its profile too clean. It bore all the hallmarks of a signal that had journeyed across cosmic distances. The turning point came when other astronomers, armed with more advanced telescopes and data processing techniques, began finding more of these mysterious flashes. With each new detection, the Lorimer burst was retroactively validated. It was no fluke. It was the first example of an entirely new class of astrophysical object. Its legacy is immeasurable. That one faint 5-millisecond spike in old data is the prototype, the genesis of an entire field of study. It forced astronomers to confront the reality that the universe is teeming with transient events of unimaginable power, phenomena that were completely invisible to us until we learned how to look for them. The Lorimer burst didn't just announce its own existence, it revealed our own ignorance, highlighting vast, violent chapters of cosmic drama playing out in milliseconds, waiting for us to finally hit play. While the search for cosmic messages is often a story of immense radio dishes and dedicated teams of scientists, one of its most intriguing chapters was written not in an observatory control room, but on the computer desks of millions of volunteers around the world. This is the story of SHB-02+14A, a signal that emerged from the largest astronomical experiment in history and quickly became one of the most tantalizing and hotly debated candidates for an artificial extraterrestrial transmission. The project was called SETI at Home, launched in 1999 by the University of California, Berkeley. Its concept was revolutionary. Instead of relying on a single supercomputer to process the mountains of noisy data from the Arecibo radio telescope, it broke the work into small chunks and distributed it across a global network of personal computers. Whenever a user's screensaver activated, their machine would get to work analyzing a tiny slice of the radio spectrum, searching for the telltale signs of a narrowband signal, the kind of focused transmission a civilization might use to broadcast its existence. At its peak, the project harnessed the combined processing power of over 1.8 million computers, creating a virtual supercomputer that was tirelessly sifting through the cosmic static for a needle in a haystack. And in 2003, it seemed they might have found one. The signal, cataloged as SETI-02+14A, appeared to check several boxes on the theoretical wish list for an intelligent transmission. Most compelling was its frequency. It was detected very close to 1,420 megahertz, the precise frequency emitted by neutral hydrogen atoms as they change energy states. This hydrogen line is considered a universal landmark, a frequency so fundamental to astronomy that any technologically advanced species would undoubtedly be aware of it. The idea, famously proposed by physicists Bernard Oliver and John Billingham, was that this would be a natural watering hole in the radio spectrum, a quiet place where civilizations from different stars might logically gather to listen and to call out. Furthermore, the signal exhibited a drift rate. This is a subtle shift in frequency over time, and it was consistent with what you might expect from a transmitter located on a planet that was both rotating on its axis and orbiting its star. The relative motion between that hypothetical world and our own telescope would cause a Doppler shift, slightly compressing or stretching the radio waves, and this signal seemed to demonstrate that exact effect. For a brief, electrifying moment, it seemed like the dream of SETI at home had been realized. The global network of home computers had seemingly triumphed, identifying a signal that perfectly matched the profile of an intelligent beacon. News outlets buzzed with the possibility, and the public's imagination was set ablaze by the prospect that our screensavers might have somehow made first contact. However, the initial excitement was soon tempered by a chorus of deep skepticism from within the scientific community. The signal, upon rigorous professional analysis, was found to be deeply problematic. The most significant issue was its incredibly low signal-to-noise ratio. It was an exceedingly faint whisper buried deep within a roaring sea of static, so weak that it constantly flirted with the threshold of what could be considered random background noise. Distinguishing a true signal from a random fluctuation in such conditions is extraordinarily difficult, and many argued that SETI-02+14 was far more likely to be the latter. Adding to the skepticism was its point of origin. When astronomers pointed their telescopes toward the patch of sky it seemed to emanate from, a point between the constellations Pisces and Aries, they found nothing. There was no nearby star, no known exoplanet, not even a discernible galaxy in that precise location. It was, for all intents and purposes, a blank spot in the universe, a deeply unsatisfying and unlikely address for an advanced civilization. Furthermore, the signal was never detected again. Despite repeated and dedicated follow-up observations, it remained a one-off event. A true interstellar beacon, designed to be found, would presumably be persistent or repeating, not a single, fleeting burst that vanishes without a trace. The final nail in the coffin for many was the signal's own behavior. The measured drift rate, initially touted as evidence, was actually erratic. It didn't follow a smooth, predictable curve as one would expect from a stable planetary transmitter. This inconsistency pointed strongly toward a more mundane explanation. The signal was probably not from deep space at all, but a product of local interference. It could have been a fleeting glitch in the complex electronics of the Arecibo telescope itself, or perhaps a reflection of a terrestrial radio transmission bouncing off a piece of space debris in orbit around Earth, creating a false signal with a misleading drift. In the end, SHB-02 plus 14I serves not as evidence of extraterrestrial intelligence, but as a powerful case study in the immense challenges of the SETI endeavor. It highlights the razor-thin line between a revolutionary discovery and an intriguing statistical fluke. It demonstrates the necessity of extreme skepticism and the rigorous process of verification that must follow any initial excitement. This signal remains a fascinating footnote, a ghost in the global machine that captivated the world, and then, just as quickly, faded back into the noise from which it came, a permanent monument to both the profound hope and the meticulous caution that defines our search for neighbors in the cosmos. But just as the allure of a nearby cosmic neighbor beckoned, another signal would capture global attention, one that seemed to originate from the most tantalizing location imaginable, right next door. The year was 2020, and the Breakthrough Listen project, a mammoth $100 million initiative to scan 1 million stars for signs of intelligence, was using Australia's venerable Parkes radio telescope. For years, this instrument had been a workhorse in the search, and in April of 2019, it spent 26 hours specifically trained on Proxima Centauri, the closest star to our Sun. It's a compelling target, a red dwarf known to host at least 2 planets, one of which, Proxima Centauri b, orbits within the star's habitable zone where temperatures could potentially allow for liquid water. The data from that observation was collected, processed, and then filed away. It wasn't until a full year later, in 2020, that a team of young researchers sifting through that archive data found something extraordinary. Buried in the observations was a narrowband radio signal, designated BLC-1, for Breakthrough Listen Candidate 1. It was a tone of 982 megahertz, and it appeared to be present only when the telescope was pointed at Proxima Centauri, vanishing when it looked away. This on-off behavior is one of the key hallmarks astronomers use to discriminate a potential celestial signal from terrestrial interference. If the signal is only there when you're looking at the target, it's far more likely to be coming from that target. The excitement within the small team was electric. This wasn't a signal from billions of light years away. This was from a mere 4.2 light years distant. The implications were staggering. As one researcher described it, it was the most significant signal they had ever found. The initial analysis was promising. The signal was narrowband, precisely the type of artificial-looking transmission a technological civilization might produce. It also exhibited a distinct frequency drift, a slight shift in its tone over time. This drift was initially interpreted as being caused by the movement of a transmitter on a planet orbiting its star, a telltale signature that would be incredibly difficult to fake. For a brief, heady moment, the world held its breath. Headlines buzzed with the possibility that we might have detected a technosignature from our closest stellar neighbor. What followed, however, was a masterclass in scientific skepticism and meticulous detective work. The Breakthrough Listen team did not announce a discovery. They announced an investigation. They knew that the history of SETI is littered with signals that initially looked perfect, but were later revealed to be human-made. Their first step was to observe Proxima Centauri again, using Parkes and other telescopes. The signal was gone. It never reappeared. This was a major red flag. A persistent beacon should, by definition, be persistent. The team then embarked on a painstaking forensic analysis, breaking down the signal's properties with excruciating precision. They discovered its fatal flaws. While the signal itself was narrowband, it was accompanied by a multitude of other tones at regular intervals, like ghostly harmonics. These sidebands are a classic fingerprint of heterodyning. a process that occurs in electronic oscillators. Essentially, the signal was leaking, and its leakage pattern pointed directly to human technology. Furthermore, the frequency drift, upon closer examination, didn't match the expected drift from a planet orbiting Proxima Centauri. Instead, it was consistent with the drift produced by a moving human transmitter, like a satellite or a vehicle on the ground. The final conclusion was definitive, if disappointing. BLC-1 was not a message from Proxima Centauri b. It was radio frequency interference, almost certainly originating from a faulty electronic device right here on Earth, possibly even on the observatory grounds itself. Its appearance and disappearance were a cruel coincidence of timing, a perfect storm of a malfunctioning gadget, and the telescope's scanning pattern that made it seem like it was only present when looking at the star. The story of BLC-1 is arguably more valuable to science than if the signal had been real. It serves as a powerful, modern case study for the immense challenge of this work. In a world saturated with our own radio emissions, filtering out the cosmic signal from the human noise is the single greatest obstacle. It underscores that the process of discovery isn't about the first exciting candidate. It's about the rigorous, often tedious, process of elimination that must follow. It proves that the scientific method, with its built-in checks and relentless skepticism, is our most powerful tool, protecting us from our own eager imaginations and ensuring that when we do finally find a signal we cannot explain away, we can truly believe it. The hunt for cosmic messages is as much a story of profound discovery as it is one of humbling mistakes, where the line between a revolutionary breakthrough and mundane human interference can be vanishingly thin. Few tales capture this delicate balance better than the dual histories of the LGM pulsar and the perplexing puritance, too, of radio astronomy's most famous cases of mistaken identity, each teaching us a crucial lesson in caution and curiosity. Our first story begins in 1967 at the Mullard Radio Astronomy Observatory in Cambridge, England. A dedicated doctoral student named Jocelyn Bell Burnell was meticulously analyzing reams of data from a new radio telescope she had helped build. The instrument was designed to study quasars, but as Bell pored over the endless paper charts, she noticed something peculiar, a faint, recurring bit of scruff that appeared in the same patch of sky at the same time every day. It was so slight that others might have dismissed it as noise, but her sharp eye and relentless attention to detail refused to let it go. She began tracking it more closely, and to her astonishment, she found it was not just random interference. It was a signal of incredible precision, a series of pulses arriving exactly every 1.337 seconds with a regularity that was almost unnerving. In an era brimming with speculation about extraterrestrial life, the immediate, thrilling, and somewhat terrifying thought was that this could be it, the first evidence of intelligence beyond Earth. The signal was so perfectly periodic that it seemed engineered. Half-jokingly, the team labeled it LGM-1 for Little Green Men. The possibility was seriously considered. After all, what natural phenomenon could possibly create such a metronomic beat across the light years? The idea of a galactic civilization using a powerful beacon to announce its presence was not just science fiction in that moment. It was a legitimate hypothesis on the table. But science, driven by skepticism and evidence, soon provided the true answer. Before any announcement was made, Bell discovered a second, similar pulsing source in a completely different part of the sky. The odds of two separate civilizations deciding to broadcast on the same radio frequency in the same pulsing manner were astronomically low. The explanation had to be natural, not artificial. The mystery was soon solved by her supervisor, Anthony Hewish, and others. They had discovered the first pulsar, a rapidly spinning neutron star, the ultra-dense, city-sized core of a star that went supernova. As this cosmic lighthouse spins, beams of radiation shoot from its magnetic poles, and if one of those beams sweeps across Earth, we see a regular pulse with every rotation. SETI 1919, as it was officially cataloged, was not a greeting card from little green men. It was the breathtaking signature of one of the universe's most extreme and fascinating objects. Jocelyn Bell Burnell's discovery was nothing short of revolutionary, opening an entirely new window into stellar evolution and earning a Nobel Prize, though famously awarded only to her male supervisor. Decades later, on the other side of the world, a different mystery was brewing that would serve as a perfect, almost comical, bookend to this lesson in humility. The Parkes radio telescope in Australia, the very instrument that had discovered the Lorimer burst, began detecting strange signals in its data. They looked, for all intents and purposes, like fast radio bursts, short, intense, and dispersed as if they had traveled across vast cosmic distances. The astronomers dubbed them Puritans, after a mythical stag that could cast a human shadow, a name reflecting their elusive and misleading nature. For years, these Puritans haunted the research. They contaminated data and fueled skepticism about the entire field of FRB research. If these signals that looked so much like cosmic events were actually local, how could anyone trust that the newly discovered FRBs were real? The team at Parkes embarked on a lengthy and frustrating detective hunt. They installed a monitoring system to watch for radio frequency interference at the telescope simultaneously with their astronomical observations. They ruled out aircraft, satellites, weather phenomena, and even ground-based lightning strikes. The Puritans remained stubbornly mysterious, their origin unknown. The breakthrough finally came through a combination of sheer luck and meticulous deduction. Researchers noticed that the Puritans only ever occurred during weekday daylight hours and never at night or on weekends. This was a huge clue. Whatever was causing them was tied to human activity on site. The final piece of the puzzle fell into place when an observatory staff member recalled that the signals often seemed to coincide with someone heating up their lunch. The team zeroed in on the facility's kitchen and its microwave oven. They discovered that if the microwave was running and someone opened the door before the timer had finished, the oven's magnetron would release a brief burst of radiation at 1400 megahertz. This burst, escaping the imperfectly sealed appliance, would hit the telescope's receiver dishes. Because the telescope's focus is not a single point but a wide field of view, the signal would appear to be dispersed, mimicking the key signature of a cosmic fast radio burst. The mighty Puritan, a data phantom that had mystified astronomers for years, was finally revealed to be the humble result of an impatient astronomer interrupting their microwave to retrieve a reheated meal. Together, the stories of LGM-1 and the Puritans form a critical chapter in the history of cosmic discovery. They are permanent reminders that the search for truth requires two equally important virtues: the boundless imagination to consider the extraordinary possibility of alien contact, and the rigorous, patient skepticism to rule out every last earthly explanation, even one as simple as a kitchen appliance. They teach us that the universe's greatest secrets are often hidden not just behind the veil of deep space, but also behind the veil of our own assumptions. While the search for fast radio bursts and potential alien beacons captures headlines, some of the most enduring mysteries in radio astronomy come from signals that defy easy categorization altogether. These aren't the brilliant, milliseconds-long screams of an FRB, but rather the subtle, strange, and stubborn whispers that linger in the data, refusing to be explained away. They are the cosmic anomalies that hint at phenomena we haven't even begun to imagine. One such enigma is known informally among researchers as the Arecibo amorphous radio blob. Detected by the legendary Arecibo telescope before its tragic collapse, This was not a point source or a brief burst, but something far more unusual, a faint, extended cloud of radio emission. It appeared as a soft, shapeless glow against the backdrop of space, with no known galaxy, nebula, or star cluster at its location. Follow-up observations with optical and infrared telescopes revealed absolutely nothing: no visible matter, no dust, no hidden object to account for the radio energy. It was a ghost, a cosmic heat signature with no body. The leading theories are as puzzling as the object itself. Could it be the faint remnant of an ancient, super low-surface brightness galaxy that is completely invisible to our current optical telescopes? Or perhaps it is the enormous halo of dark matter surrounding a failed galaxy, somehow interacting in a way that produces this faint radio whisper. The blob remains a profound reminder that our maps of the universe are still incomplete, and that vast, invisible structures might be lurking just beyond the edge of our perception, waiting for more sensitive instruments to bring them into focus. Then there are the Puritans that got away. While the microwave oven explanation solved the mystery for the majority of these signals, a small, stubborn subset refused to be pinned down. These anomalous Puritans shared the dispersed frequency sweep characteristic of an astrophysical source, but they occurred at times when the observatory's microwave was confirmed to be off, and under atmospheric conditions that ruled out aircraft or weather-related interference. Their signatures were slightly different from the microwave-generated ones, often broader in bandwidth or originating from a different point in the sky. These outliers present a fascinating possibility that there might be multiple types of Puritans. Some are, undoubtedly, our own technology interrupting the cosmic silence. But could others be a genuine, albeit terrestrial, atmospheric phenomenon that we simply do not understand? They might be caused by rare and specific types of lightning high in the ionosphere, or by energetic particles from the sun interacting with the upper atmosphere in an unusual way. These unexplained Puritans are a critical cautionary tale. They prove that even after we think we've solved a mystery, a few pesky data points can remain, whispering that there's more to the story. Perhaps most tantalizing for those who search for intelligence are the signals that look almost, but not quite, right. Buried deep within the vast archives of SETI surveys are recordings of what researchers call slow-drifting narrowband signals. These are not the dramatic bursts of an FRB or the powerful, static blips of a pulsar. They are faint, continuous tones that drift very slowly in frequency over time. This drift is key. Natural astrophysical sources don't produce pure, narrowband signals. They're either broad spectrum or pulsed, and human-made radio frequency interference typically has a very fast, erratic drift caused by the motion of satellites or aircraft. These slow drifting signals, however, exhibit a drift rate that is perfectly consistent with what you would expect from a transmitter on a planet with a slow rotation, like Mars or Earth. It's the exact signature a technosignature might have. The problem is that these signals are always found after the fact, in old data. By the time researchers identify one, it's too late to point other telescopes at that location to confirm it. There are ghosts in the recording, impossible to verify and therefore impossible to validate. They could be a previously unknown type of very subtle, very slow astrophysical maser, a natural laser operating at radio frequencies. Or they could be an exotic form of interference from a piece of technology whose transmission properties we don't fully comprehend. But they also represent the most frustrating and exciting possibility of all, that our first detection of a signal from another civilization might not be a powerful, obvious beacon, but a faint, fleeting whisper that we recorded once and then spent decades trying to understand, a message that arrived and was almost immediately lost again in the endless sea of noise. While our journey so far has focused on mysterious signals actively reaching us, some of the most compelling cosmic puzzles are defined not by what we hear, but by a profound and telling silence. This brings us to the enigma of KC 8462852, better known as Boyajian star, or more popularly, Tabby's star, named after the astronomer Tabitha Boyajian, who first brought its bizarre behavior to light. This otherwise ordinary star, nestled in the constellation Cygnus and located about 1,470 light-years away, became an interstellar celebrity not for any signal it was sending, but for the strange, monstrous shadows it seemed to be casting. The discovery was made by NASA's Kepler Space Telescope, an observatory designed to find exoplanets by watching for the telltale, periodic dimming of a star as a planet passes in front of it. Kepler monitored the brightness of over 150,000 stars, and while most exhibited predictable, repeating dips, Boyajian's star stood out as a spectacular outlier. Its light curve was chaotic and inexplicable. There were small, frequent flickers, but also massive, irregular dips where the star's light would plummet by up to 22%, a staggering amount. To block that much light would require an object far larger than a planet, something roughly half the width of the star itself. Furthermore, these dips were not periodic. They occurred at random intervals and lasted for wildly different lengths of time, from days to weeks. It was as if something was sporadically and haphazardly moving in front of the star, but on a scale that defied any conventional explanation. The scientific community scrambled for answers, and the theories ranged from the natural to the extraordinary. Perhaps a massive, fragmented family of comets was orbiting the star in a tight, chaotic swarm, creating a irregular veil of dust and gas. Maybe the star had recently consumed a planet, sending enormous clouds of debris into a chaotic orbit, but the most captivating and admittedly most speculative theory came from the realm of science fiction, the idea of a Dyson swarm. This hypothetical megastructure, proposed by physicist Freeman Dyson, is a vast collection of energy capturing satellites or platforms that an advanced civilization might build around its star to harness its entire energy output. The irregular, massive dimming patterns of Tabby's star seemed, to some, eerily consistent with the construction phases of such an immense artificial project, with different segments of the swarm occasionally blotting out the light. This startling possibility catapulted the star from an astrophysical curiosity to a prime SETI target. If such incredible engineering was indeed underway, there should be other evidence. An advanced civilization operating on that scale would undoubtedly produce waste heat, a detectable infrared signature, or perhaps even leak powerful radio communications. The world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Allen Telescope Array in California, were swiftly aimed at KC 8462852. They listened intently across a wide range of frequencies, searching for the narrowband hum of a deliberate beacon or the broadband crackle of immense industrial activity. The result, after extensive and repeated observation, was a uniform and deafening silence. No anomalous radio signals were ever detected. Subsequent infrared observations also failed to find the excess heat that an energy-harvesting megastructure would radiate. This non-detection is, in its own way, just as significant as a detection. It forces a rigorous re-evaluation of the megastructure hypothesis. While it doesn't completely rule it out, perhaps the civilization is using technology we can't conceive of, or is deliberately hiding its emissions. It makes the possibility far less likely. The weight of evidence began to swing back toward natural explanations. The most promising theory now points to an enormous cloud of exceptionally fine dust. Detailed follow-up studies found that the star dims more at blue wavelengths than at red ones. This is a classic signature of light scattering off tiny dust particles, which tend to block blue light more effectively. A massive, uneven ring of micron-sized dust grains, perhaps the remnants of a cataclysmic collision between planets or moons, could account for the erratic and deep dimming events without the need for alien engineering. The silence from the radio telescopes, therefore, isn't a disappointment. It's a crucial data point. It tells us that while the universe is capable of producing astoundingly strange and beautiful natural phenomena, it has not yet offered us clear proof of other builders among the stars. The mystery of Tabby's star endures, not as a potential alien megastructure, but as a powerful lesson in how the most thrilling cosmic discoveries often begin with a shadow and are ultimately understood not by what we find, but by what we diligently and definitively do not. Yet even as the silence from Tabby's star deepened, another cosmic whisper was causing a very different kind of stir, one that perfectly illustrates the powerful pull a single, promising signal can have on our collective imagination. Our journey now takes us to the Gliese 581 system, a red dwarf star just over 20 light-years away in the constellation Libra. By 2008, this star was already a celebrity in the exoplanet community, known to host a family of at least 4 planets. One of them, Gliese 581g, was a particularly tantalizing candidate. It was a rocky world orbiting squarely within the star's habitable zone, a place where temperatures could theoretically allow for liquid water to pool on its surface. It was, in essence, one of the first potentially Earth-like worlds discovered in our immediate galactic neighborhood, a prime address in the search for life. It was against this backdrop of excitement that an Australian team from the University of New South Wales made an announcement that sent shockwaves through the media. While using a telescope in Tasmania, they claimed to have detected a suspicious signal emanating from the precise direction of the Gliese 581 system. The signal itself was a single, isolated burst, a brief blip that stood out from the background noise. In the cautious language of science, the researchers were careful not to claim a discovery, but the implication was clear enough to be seized upon. The news spread like wildfire. Headlines around the world blared that we may have received a message from an alien civilization next door, a call from a potentially habitable world. The public fascination was immediate and intense. The idea was intoxicatingly simple. A promising Earth-like planet had been found, and now, seemingly, a signal had arrived from that very spot. The timing felt almost too perfect to be a coincidence. For a brief period, the Gliese 581 signal became a global sensation, a symbol of the thrilling possibility that first contact might be just around the corner, emanating from a star we could almost see with the naked eye on a clear, dark night. But the scientific process, with its built-in mechanisms for skepticism and verification, quickly swung into action. Other radio astronomy groups around the world, from the SETI Institute's Allen Telescope Array to the massive Green Bank Telescope, immediately pointed their dishes toward Gliese 581. They listened intently, scanning across a wide range of frequencies. The result was a uniform and definitive silence. No signal was ever detected again. This failure to replicate was the first and most critical red flag. A genuine interstellar beacon, especially one powerful enough to be detected across 20 light-years, would almost certainly be persistent or repeating, not a single one-off event. The next phase was a deep forensic analysis of the original Australian data. Independent experts began to pick apart the signal's characteristics, and they soon found its fatal flaws. The most telling detail was the signal's modulation. It exhibited a pattern that was inconsistent with what would be expected from a source moving through space. Instead, its properties were classic fingerprints of local, terrestrial radio frequency interference. The most likely culprit, it was determined, was a phenomenon called intermodulation distortion. This occurs when two or more strong radio signals from human sources, perhaps a nearby radio station, and a military radar installation, mixed together unintentionally within the slightly non-linear electronics of the telescope's own receiver. This mixing can create a ghost signal, a phantom transmission that appears at a completely new frequency. In this case, the mathematics showed that the frequency of the alleged alien signal was the exact difference between two powerful, known terrestrial transmitters. It was a perfect storm of electronic chaos that created a convincing cosmic mirage. The Gliese 581 incident rapidly transformed from a potential breakthrough into a sobering case study. It underscored a harsh and ever-present reality for radio astronomers. Our planet is drowning in a sea of our own radio emissions, filtering the faint, distant whispers of the cosmos from the roaring static of our own civilization is the single greatest technical challenge in the search for extraterrestrial intelligence. This event served as another crucial lesson in the absolute necessity of confirmation. A detection by a single telescope, no matter how promising, is not a discovery. It is merely a candidate, a hypothesis that must be ruthlessly tested by independent observers using different instruments before it can ever be taken seriously. In the end, the signal wasn't a message from Gliese 581G. It was a message to us, a reminder of the rigorous patience and profound caution required in this field. It showed how easily our own technology can mimic the signs we so desperately hope to find, and how our eagerness for discovery can sometimes outpace the slow, meticulous grind of scientific proof. The story of the Gliese 581 signal is not one of failure, but of a process working exactly as it should, protecting us from our own excitement and ensuring that when a signal finally does arrive that passes every test, we can truly believe it. And just as the Gliese 581 story was settling into the annals of scientific near-misses, another signal rose to take its place, demonstrating just how persistent this cycle of excitement and explanation can be. In the spring of 2015, the Rattan 600 radio telescope, a unique and massive ring of reflecting panels nestled in the Caucasus Mountains of Russia, recorded something peculiar. The data from that observation sat largely unnoticed for over a year until, in the summer of 2016, an anonymous astronomer shared the details with a small email list of SETI enthusiasts. From there, the news exploded into the public sphere, igniting a fresh wave of speculation around a star known as HD 164595, located approximately 95 light-years away in the constellation Hercules. This star holds a compelling profile for anyone searching for cosmic company. It's a sun-like star, broadly similar to our own, and is known to host at least one Neptune-sized planet. While this known world orbits far too close to its star to be habitable, the possibility of other, as yet undiscovered planets in more temperate orbits made the system a worthy target for observation. The signal detected by Rattan 600 was a powerful narrowband burst at 11 GHz. Its intensity was a primary source of the immediate intrigue. If this signal were indeed an isotropic broadcast, a transmission radiating equally in all directions like a bare light bulb, it would require a power source far beyond anything human civilization could muster, harnessing the entire energy output of a planet to fuel its transmitter. The alternative possibility, however, was even more mind-bending. If it were a tightly focused beacon, deliberately aimed in our direction, the required energy would be vastly reduced, falling within the realm of a Kardashev Type II civilization capable of harnessing the total energy of its star. For a brief, electrifying moment, it seemed we might be listening in on a conversation between stellar neighbors. The SETI community, now well practiced in responding to such announcements, did not wait. Within 24 hours of the news breaking publicly, the Allen Telescope Array in Northern California was commanded to drop its scheduled observations and train its 42 dishes on HD 164595. For 2 consecutive days, the dedicated SETI facility scanned the star system across a wide range of frequencies, listening for any sign of a repeat transmission or other anomalous activity. The result, however, was a now familiar silence. No signal was found. The initial excitement, which had rippled through news outlets and social media, rapidly began to deflate as this critical lack of confirmation set in. The swift and thorough follow-up investigation quickly uncovered the signal's more likely and far more terrestrial origins. Astronomers noted that the signal's frequency, 11 gigahertz, falls within a portion of the radio spectrum that is heavily used for military and satellite communications here on Earth. The most plausible explanation, widely accepted by the scientific community, is that the Rotan 600 telescope intercepted a burst of transmission from a secretive military satellite. The unique design of the Russian telescope, with its stationary curved reflector and a moving receiver, makes it particularly susceptible to picking up signals from objects moving through the sky above it. A satellite passing through its wide field of view could easily have created a fleeting, strong signal that appeared to originate from a fixed point in the deep sky, a classic illusion caused by the telescope's own operational characteristics. The story of the HD 164595 signal is a perfect modern echo of the Gliese 581 incident. It reinforces a critical and somewhat humbling pattern in the search for extraterrestrial intelligence. Our most promising detections have an uncanny habit of dissolving into the mundane reality of our own technological footprint. Each event serves as a masterclass in the scientific method, demonstrating the crucial difference between an initial detection and a verified discovery. It highlights the essential role of independent verification and the community's growing sophistication in rapidly deploying resources to investigate potential leads. While the outcome was another false alarm, the process itself is a testament to the field's rigor, ensuring that when a signal finally arrives that cannot be explained away by a passing satellite or a faulty microwave, we will be ready to recognize it for what it truly is. In the turbulent history of cosmic false alarms, one signal stands out not for its brief flash of fame, but for its stubborn refusal to disappear entirely. This is the curious case of the so-called Tau Booty signal, a persistent ghost that haunted the edges of SETI research for years. Unlike the one-off blips that could be easily dismissed as glitches, this one had a peculiar and tantalizing characteristic. It was reportedly detected not just once, but on multiple occasions throughout the 1990s. The source of this intrigue was the Tau Booty system, a binary star system a mere 51 light-years away, home to a massive, Jupiter-like gas giant planet that orbits scorchingly close to its parent star. The initial claims, primarily put forward by a team led by astronomers from the University of Western Sydney, and later by researchers at the highly respected Lick Observatory, were undeniably alluring. They reported detecting a strong, narrowband radio signal at a frequency of 1,420 megahertz, the hallowed hydrogen line, that universal watering hole. Even more compelling was the signal's apparent modulation. It seemed to vary in a way that was synchronized with the orbit of the known hot Jupiter planet, Tau Booties b. This suggested a breathtaking possibility that the signal wasn't just coming from the general vicinity of the star, but was somehow tied to the planet itself. The implication was that we might be detecting not a deliberate broadcast, but leakage, the inadvertent radio chatter of a technologically advanced society living on or around that alien world. For a time, the Tau Booties signal generated a palpable buzz. Here was a candidate that seemed to check so many boxes: a nearby star system, a repeating signal, and a potential correlation with a known exoplanet. It wasn't a single, fleeting shout into the void. It was a whisper that seemed to keep coming back, begging for attention. The idea captivated the public imagination and sparked intense debate within the small community of SETI scientists. It felt like a puzzle that, if solved, could crack the entire mystery open. However, the cornerstone of the scientific method is not initial detection, but independent verification. This is where the story of the Tau Booty signal takes a definitive turn. The broader astronomical community, armed with some of the world's most powerful radio telescopes, turned their collective gaze toward the system. Teams from the SETI Institute using the Allen Telescope Array, researchers at Green Bank, and astronomers at the giant Arecibo dish in Puerto Rico all conducted dedicated, high-sensitivity searches for the signal. Despite their best efforts, using equipment far more sophisticated than what was available during the initial reports, not a single one of these follow-up observations could replicate the finding. The signal had vanished, leaving only the empty static of space. The overwhelming consensus that emerged was one of profound skepticism. Without verification, the original detections were increasingly viewed as likely artifacts of radio frequency interference, a phantom generated by the ever-growing cacophony of human technology. Critics pointed out that the modulation pattern, once hailed as a key clue, could also be explained by the periodic rotation of a terrestrial source, like a satellite in a geosynchronous orbit, whose transmission beam might sweep across the telescope at regular intervals. The signal's persistence, rather than strengthening its case, actually made it more suspicious. A true interstellar signal would be subject to the vagaries of the interstellar medium, which can cause scintillation and fading, making a signal that appears with perfect regularity for years on end seem less, not more, likely to be genuine. Thus, the Tau Booty's signal gradually faded from serious scientific consideration, becoming a fascinating footnote in the annals of SETI. Its legacy, however, is far more valuable than if it had been real. It serves as a masterclass in the critical need for reproducibility. In a field so prone to excitement and speculation, it underscores the indispensable role of cold, hard skepticism. A detection, no matter how promising, is merely an anecdote until it can be confirmed by multiple independent observers. This process, while it can be frustrating and often deflating, is the very engine that drives science forward, separating wishful thinking from tangible discovery. The ghost of Tau Booties remains a powerful reminder that in the search for truth, our most important tool is not just the telescope that first hears a whisper, but the entire global network of instruments and minds dedicated to listening again and again to ensure that what we think we heard was truly a voice from the stars. While the hunt for radio whispers and interstellar beacons often feels like listening for a single voice in a roaring stadium, some of the most compelling mysteries are found not by listening, but by watching. This brings us to an enigma discovered by the Kepler Space Telescope, an instrument that revolutionized our understanding of planets by staring unblinkingly at the light of distant stars. Among the hundreds of thousands of light curves it meticulously recorded, one star stood out not for its dramatic dimming, but for the bizarre and unsettling shape of its shadows. This is the mystery of KC 5520878. Like Tabby's star, KC 5520878 was an otherwise normal star that began acting in a profoundly abnormal way. Kepler's primary mission was to detect the telltale, symmetrical dips in starlight caused by a planet passing in front of its host star. These transits create a clean, U-shaped curve. The light smoothly decreases as the planet moves onto the star's face, holds steady during the full transit, and then smoothly increases as the planet exits. But the dips from this star were nothing like that. They were messy, jagged, and deeply asymmetric. The light would often drop precipitously, but then rise back up in a completely different pattern, sometimes with a steep incline and a slow decline, or vice versa. It was as if the object blocking the light was not a solid, spherical planet, but something irregular, dynamic, and constantly changing shape. Astronomers were left scratching their heads, and the theories that emerged were as strange as the data itself. The leading natural explanation pointed to a catastrophic and ongoing disintegration. Imagine a planet orbiting perilously close to its star, a scorched world being slowly torn apart by the immense gravitational forces and blistering stellar radiation. This could create a vast, comet-like tail of dust and vaporized rock trailing behind the planet. As this disintegrating world and its chaotic debris cloud passed in front of the star from our vantage point, it would produce exactly the kind of irregular, asymmetric dimming that was observed. The light curve wouldn't be a clean dip. It would be a messy, shifting profile that changed with every orbit as more material was boiled away and the tail evolved. Another compelling theory suggested a warped, clumpy debris disk, a vast ring of dust and planetesimals, perhaps shepherded by the gravitational pull of an unseen planet that was tilted and uneven, casting a complex and variable shadow. Yet, the sheer strangeness of the signal inevitably invited a more speculative question. Could such a bizarre, structured, and anomalous shadow be artificial? While a megastructure like a full Dyson sphere seemed unlikely for a star showing no other signs of being engineered, perhaps a more partial or novel construction could account for the peculiar light curve. The possibility, however remote, was enough to pique the interest of the SETI community. If there was any chance that this unprecedented stellar behavior was linked to astroengineering, then it deserved a dedicated listen. Radio astronomers swiftly added KC 5520878 to their target list, pointing powerful dishes like the Green Bank telescope toward its coordinates. They searched for the hallmarks of technology, narrowband signals that could be a deliberate beacon, or broadband leakage that might indicate industrial activity supporting such a massive project. The result, after extensive observation, was the same profound silence that has met so many other tantalizing candidates. No anomalous radio signals were ever detected. This null result is far from meaningless. It actively shapes our understanding of the mystery. While it doesn't rule out the disintegrating planet or warped disk theories, natural processes don't need to broadcast radio waves. It does make a technological explanation significantly less probable. The absence of a technosignature reinforces the idea that we are witnessing a rare and violent natural astrophysical process, one we are still working to fully comprehend. The case of KC 5520878 thus becomes a powerful example of a different path in the search for intelligence, not just listening for signals, but also scanning the skies for anomalies, and then using all the tools at our disposal, including the failure to find associated radio emissions, to help rule out the most extraordinary possibilities. It demonstrates that sometimes the most valuable discovery is understanding what something is not, allowing us to focus our imagination on the even more incredible realities of a universe capable of creating such magnificent and destructive natural wonders. While our attention has been largely drawn to the vast distances beyond our galaxy, some of the most head-scratching signals are being broadcast from our very own cosmic backyard, emanating from the turbulent and mysterious heart of the Milky Way. This brings us to a peculiar family of signals known as galactic center radio transients, or GCRT. Unlike the millisecond screeches of extragalactic fast radio bursts, GCRT are a slower, more methodical class of mystery. They are bright, repeating bursts of radio waves that originate from the dense, chaotic environment surrounding Sagittarius A star, the supermassive black hole at the center of our galaxy. The patriarch of this strange family is GCRT J1745-3009. It was first detected in 2002 by the Very Large Array Radio Telescope in New Mexico, and its behavior immediately set it apart from anything else in the astronomical catalog. This source doesn't just flash and vanish. It erupts into brilliance for approximately 10 minutes, and it does so with a remarkable regularity, bursting roughly every 77 minutes before fading back into the background noise. It's a cosmic geyser, pumping out immense pulses of radio energy on a schedule we can almost set our watches to. Since its discovery, a handful of other objects with similar, though not identical, bursting behavior have been identified in the same region, forming a small but significant family of galactic mysteries. The location of these transients is the first major clue to their identity. The galactic center is an extreme environment, a crowded metropolis of stars, gas, and powerful magnetic fields, all whirling around the immense gravitational pull of a 4 million solar mass black hole. This is a place where normal physics is pushed to its breaking point, and it is the perfect laboratory for generating bizarre and energetic phenomena. The leading theories for what creates the GCRT are as exotic as their home. One compelling idea centers on a type of binary star system, but not a typical one. This would involve a highly magnetic white dwarf star and a much larger, cooler red dwarf companion. As they orbit one another, the white dwarf's powerful magnetic field could funnel material from the red dwarf, channeling it down onto its poles in immense, raging rivers of plasma. This process could create a natural electric generator, or unipolar inductor, capable of producing staggeringly powerful, periodic bursts of coherent radio emission that sweep across our field of view like a lighthouse beam. Another strong candidate is a class of ultra-long-period magnetars. We know magnetars can produce fast radio bursts, but perhaps in the unique environment of the galactic center, some magnetars have even more powerful and twisted magnetic fields that allow them to produce these slower, repeating eruptions. The 77-minute period could represent the spin rate of this highly magnetized neutron star, though that would make it an incredibly slow spinner compared to most of its kind. A third theory delves into the black hole itself, suggesting these bursts could be caused by flares from material interacting with the black hole's intense magnetic field as it spirals toward its doom, or perhaps from asteroids or small planets being torn apart by the black hole's tidal forces. The true nature of the GCRT remains one of the most engaging puzzles in galactic astronomy. They are a different kind of mystery than the FRBs from billions of light years away. These are homegrown enigmas, occurring in our own neighborhood, yet proving just as difficult to decipher. They remind us that even in our own galactic core, there are forces and objects at work that we are only beginning to recognize, a hidden layer of cosmic activity playing out in the shadow of the monster that reigns at the center of our Milky Way. Of course, the universe is a master of illusion, and sometimes the most convincing cosmic whispers turn out to be nothing more than the echo of our own technological chatter. This brings us to a crucial and often unsung chapter in the story of fast radio bursts, the imposters. These are signals that, for a brief and tantalizing moment, fooled even the most experienced observers, perfectly mimicking the key characteristics of an FRB before being unmasked by the meticulous detective work of radio astronomers. Their stories are a testament to the fact that in the modern era, the greatest challenge isn't always hearing a signal, it's proving it didn't come from Earth. One of the most pervasive and frustrating sources of false FRBs is something known as peridans, but not the kitchen microwave kind we discussed earlier. These are a more sophisticated and elusive class of imposter. A particularly compelling case emerged from data collected by the Parkes Radio Telescope, where signals were detected with all the hallmarks of a genuine cosmic burst. They were dispersed, meaning the higher frequencies arrived before the lower ones, and they appeared to come from a wide range of directions in the sky. For a time, they were serious candidates. The breakthrough in cracking this case didn't come from looking up, but from looking around, astronomers installed a new real-time radio frequency interference monitoring system at the observatory. This system acted like a security camera for radio noise, constantly logging all the human-made transmissions in the area. They soon discovered that these specific peritons occurred at the exact same time as powerful radar pulses from the nearby Australian Defence Force airport. The radar itself wasn't the direct culprit. The problem was more subtle. The incredibly powerful radar pulses were reflecting off the aircraft they were tracking. These reflections would then bounce off the ground or other objects and finally enter the giant, sensitive bowl of the park's telescope. The path the signal took bouncing off a fast-moving object imparted a frequency sweep that perfectly mimicked the dispersion of a signal traveling through intergalactic space. It was a cosmic mirage created by the marriage of cutting-edge military technology and the laws of radio wave reflection. Another classic imposter comes from much closer to home, literally in orbit above us. The problem of satellite downlinks is a growing headache for radio astronomy. Communication satellites, particularly those in geostationary orbit, are constantly beaming vast amounts of data down to Earth. Normally, a radio telescope can filter these out because they are constant, known sources. The trouble begins when something temporarily illuminates a satellite, causing a brief, brilliant flash of radio energy. A primary culprit is the sun. When a satellite emerges from the Earth's shadow into full sunlight, its solar panels can generate a sudden surge of power. If this power surge causes a transmitter to activate or a component to resonate, it can release a short, intense burst of radio waves. From the perspective of a ground-based telescope, this looks exactly like a dispersed pulse from deep space. It's brief, it's powerful, and because the satellite is moving relative to the telescope, the signal acquires a frequency drift that looks for all the world like the dispersion measure of an extragalactic source. Telling this apart from a real FRB requires exquisite timing and precise orbital data to confirm that a known satellite was in the right position at the right time to create the illusion. Perhaps the most insidious imposters are the ones born within the telescopes themselves. Modern radio observatories are miracles of complex electronics, with miles of wiring, countless amplifiers, and sophisticated digital signal processors. This complexity can sometimes turn back on itself. A phenomenon known as intermodulation distortion occurs when two or more strong, legitimate radio signals, perhaps from a local FM station and an aircraft transponder, enter the telescope's receiver system. If the electronics operate even slightly outside their perfectly linear range, these signals can mix, creating a new, phantom signal at a completely different frequency. This ghost signal will inherit properties from its parents, and under the right conditions, can appear as a solitary, dispersed pulse that seems to have no terrestrial source. Astronomers have to become electrical engineers, tracing the phantom back to its source by identifying the two original transmissions whose mathematical difference creates the frequency of the imposter signal. The process of weeding out these false alarms is a painstaking forensic science. It requires a multi-telescope approach. If a signal is truly cosmic, it should be detected by other radio dishes across the world that are also pointing at that part of the sky. If only one telescope hears it, the cause is almost certainly local. It also requires a deep understanding of the local radio environment, a catalog of every transmitter, satellite, and radar installation for hundreds of miles. Each potential FRB candidate is put through this rigorous gauntlet, and the vast majority are dismissed. This behind-the-scenes work is unglamorous and rarely makes headlines, but it is the essential foundation that gives the remaining unexplained signals their profound significance. Every time an imposter is unmasked, it doesn't represent a failure. It sharpens our tools and refines our search. ensuring that the signals that survive this intense scrutiny are the ones truly worth believing in. But what if the most profound cosmic mystery isn't a fleeting signal from a single point in space, but a vast, silent current pulling at the very fabric of the universe itself? This brings us to one of the most controversial and mind-bending concepts in modern cosmology, an anomaly so grand it challenges our understanding of everything, the phenomenon known as dark flow. Unlike the blips and bursts from stars and galaxies, this isn't a signal we can point a single telescope at. It is a ghostly drift, a subtle pattern etched into the aftermath of the Big Bang itself, suggesting that our entire observable universe might be caught in a cosmic river flowing towards something unimaginable beyond its horizon. The story begins with the cosmic microwave background, or CMB, the faint echo of the universe's fiery birth. This faint glow, visible in every direction, is the oldest light we can see, a snapshot of the cosmos when it was just 380,000 years old. For the most part, this radiation is incredibly uniform, but it contains tiny millionth of a degree fluctuations, the seeds from which all galaxies and clusters would eventually grow. In the early 2000s, a team of astronomers led by Alexander Kashlinsky made a startling claim. By carefully studying the data from NASA Wilkinson Microwave Anisotropy Probe, they argued that these tiny temperature fluctuations weren't entirely random. They suggested that a huge number of massive galaxy clusters appeared to be moving together in a coordinated stream, all hurtling toward a particular patch of space between the constellations Centaurus and Vela at a staggering velocity of nearly 1,000 kilometers per second. This motion was separate from the universe's overall expansion. It was a peculiar velocity on a truly colossal scale. They called this coordinated motion the dark flow. The implications of such a discovery were, and remain, revolutionary. According to the standard model of cosmology, the universe is homogeneous and isotropic on large scales, meaning it should look roughly the same in all directions, and there should be no preferred direction of motion. The gravitational tug of all the matter within our observable universe should be the only force acting on these galaxy clusters. The dark flow suggested something was wrong. The sheer number and mass of the clusters moving in unison implied a gravitational pull so immense that it couldn't possibly be coming from anything we can see. The most breathtaking and unsettling explanation was that this flow was being caused by the gravitational influence of something entirely outside our observable universe. Perhaps our universe is just one bubble in a vast multiverse, and the gravity from another, incredibly massive bubble universe beyond our cosmic horizon is tugging on everything within our sight, drawing us toward it like a magnet. Naturally, a claim this extraordinary was met with intense skepticism and fierce debate. Critics argued that the signal was at the very edge of detectability and could be an artifact of the measurement technique itself, a systematic error in how the CMB data was being processed and interpreted. The astronomical community waited for more data, and it arrived in the form of the Planck satellite, a European Space Agency mission designed to map the CMB with unprecedented sensitivity and resolution. When the Planck team analyzed their data for this specific effect, they reported a null result. They found no significant evidence for a dark flow, arguing that the earlier detection was likely contaminated by other signals, like emissions from our own galaxy that hadn't been perfectly subtracted out. This seemed, for a time, to be the end of the story. Yet, like a true cosmic mystery, it refused to die. Kashlinsky and his team reanalyzed the very same Planck data using their own different methodology and came to a completely opposite conclusion. They argued that the Planck data, when processed their way, not only confirmed the dark flow, but suggested it extended even farther than they had originally thought. The debate now was no longer just about physics. It was about statistics and data analysis pipelines. a highly technical argument happening in the pages of scientific journals. This left the cosmology community deeply divided. One side saw a fascinating but ultimately unproven anomaly that would likely vanish with better data. The other saw a stubborn signal that refused to go away, a clue pointing toward a fundamental incompleteness in our standard model of the universe. While dark flow is not a radio signal in the traditional sense, it perfectly embodies the spirit of our search. It is a pattern, a signal in the most fundamental data we have about the cosmos, whispering of forces and structures operating on scales we can scarcely conceive. It challenges the Copernican principle that we do not occupy a special place in the universe, suggesting instead that we might be caught in a vast cosmic current, pulled by the invisible hand of something from beyond our horizon. Whether this flow is ultimately proven to be real or dismissed as a measurement error, its legacy is secure. It forces us to look past the edge of our map and wonder what unimaginable lands might lie in the terra incognita of the greater cosmos. While our gaze is often fixed on the deepest reaches of intergalactic space, some of the most convincing cosmic mirages are generated much closer to home, born from the turbulent and dynamic environment of our own star. This brings us to a pervasive and often misunderstood source of interference that has masqueraded as a deep space signal, the phenomenon rooted in the Sun's own magnetic architecture, known as the Parker spiral. Unlike a fleeting burst from a malfunctioning microwave, this is a fundamental and constant feature of our solar system, a grand structure of invisible lines that can whisper false promises to our most sensitive radio ears. To understand this cosmic illusion, we must first picture the solar wind. The sun is constantly blowing a supersonic torrent of charged particles, protons, and electrons, outward in all directions. But the sun is also rotating, and this rotation twists its powerful magnetic field into a shape first predicted by physicist Eugene Parker. Imagine a child spinning on a playground, holding a garden hose that's spraying water. The water streams don't shoot out in straight lines. They spiral outward from the spinning source. In exactly the same way, the sun's magnetic field is dragged by its rotation into a vast Archimedean spiral that fills the entire solar system, a structure so immense that Earth and all the other planets orbit within its swirling arms. This is the Parker spiral, the invisible backbone of the heliosphere. This spiraling magnetic field does more than just guide the solar wind. It acts as a powerful natural particle accelerator. Electrons, being incredibly light, can get caught in these magnetic field lines and be accelerated to nearly the speed of light. As these ultra-relativistic electrons are forced to spiral along the magnetic fields, they emit radiation across a broad spectrum, including strong, coherent bursts of radio waves. This type of emission is known as type Roman 3 radio bursts. To a radio telescope on Earth, these bursts can be incredibly convincing. They are dispersed, meaning the higher frequency components of the burst arrive before the lower frequencies, creating that classic sweeping signature across a receiver. This dispersion is not caused by traveling through intergalactic space, but by moving through the turbulent, electron-rich plasma of the sun's own corona and the solar wind itself. The effect, however, can look eerily similar to a signal that has journeyed across millions of light years. The most telling clue that often gives away a type Roman 3 burst is its characteristic frequency drift. Because these radio waves are generated at different heights in the sun's corona, where higher frequencies are produced in the denser plasma closer to the surface and lower frequencies in the thinner plasma farther out, the signal appears to drift rapidly downward in frequency. An astronomer seeing this on a spectrogram watches the signal streak from high to low frequency in a matter of seconds. This fast, steady drift is a classic fingerprint of a solar event. A genuine extraterrestrial signal, unless it were coming from a source moving at a truly implausible velocity would not exhibit such a rapid and smooth drift. It's this very property that allows modern signal processing software to automatically identify and flag these events, filtering out the voice of our own star to better hear the faint whispers from beyond. The learning process to reach this point of understanding was not without its moments of confusion. In the early days of radio astronomy, before the Parker spiral was fully understood and its radio signatures were cataloged, a strong type Roman 3 burst could easily cause a stir. One notable historical example occurred during the nascent years of the search for extraterrestrial intelligence. A powerful, drifting signal was detected that seemed to possess several desirable qualities, leading to a brief period of intense interest and analysis. It was only through careful correlation with solar observatories that astronomers were able to definitively link the event to a major solar flare and the subsequent storm of particles racing out along the spiral magnetic fields. This event, and others like it, served as a crucial lesson. Before pointing to the cosmos, one must first look toward the sun. The process of weeding out these solar imposters has now become a standard and critical part of the DATA Chinese letter pipeline for every major SETI project and radio astronomy survey, a silent tribute to the complex and beautiful physics of our own celestial backyard. Yet for every cosmic scream with a known origin, there exist whispers that stubbornly refuse to be categorized, signals that behave in ways that challenge our existing labels and force us to reconsider what might be possible. Welcome to the world of the unexplained repeaters, a menagerie of radio oddities that don't play by the established rules of pulsars or fit the profile of fast radio bursts. Among these, few are as peculiarly captivating as the signals that seem to come back, not with a predictable clockwork rhythm, but with the irregular, haunting cadence of an echo. Take, for instance, a phenomenon some researchers have informally dubbed the boomerang signal. Unlike the repeating FRB with its 16-day cycle or the 77-minute pulse of a galactic center transient, the boomerang operates on its own mysterious timetable. It might erupt with a powerful burst of radio energy, then fall completely silent for months or even years, only to suddenly return with an almost identical signature. This long and irregular delay is the core of its mystery. A magnetar starquake or a pulsar's rotation creates patterns we can eventually decipher, but the boomerang's return feels almost random, like a solitary caller who only picks up the phone when we least expect it. Classifying such an erratic source is a monumental challenge for astronomers. The first and most difficult task is simply catching it in the act, not once, but multiple times, to confirm it is indeed the same object and not a series of similar but unrelated one-off events. This requires immense patience and the dedicated archiving of vast amounts of sky survey data, so that when a new burst is detected, scientists can sift through decades of old observations to see if that same patch of space has ever flared up before. When a match is found, the real detective work begins, and the theories proposed to explain such long and variable delays are as fascinating as they are varied. One compelling natural explanation involves the concept of gravitational lensing. Imagine a massive, invisible cloud of cold gas and dust drifting through interstellar space between us and the source of the burst. This cloud could act like a cosmic magnifying glass, but for radio waves. As the cloud moves, its gravitational field bends and focuses the radio emissions from a persistent source behind it. From our viewpoint on Earth, the source would seem to suddenly flash into brilliance only when the lensing cloud passes directly through our line of sight, amplifying the signal enough for us to detect it. The irregular timing of the bursts wouldn't be due to the source itself, but to the unpredictable motion of this invisible lens drifting in the foreground. It would be like a distant lighthouse whose light is only visible to us when a ship sails perfectly between us, its masthead light perfectly aligning with the distant beam for just a moment. Other theories look to more complex behaviors of the source object itself. Perhaps we are witnessing a highly magnetized neutron star with an extremely slow and wobbly precession. Precession is the gradual change in the orientation of a rotating object's axis, like a spinning top slowly tracing a circle as it winds down. For a neutron star, this could mean its powerful radio beams might only sweep across Earth's location in the galaxy at irregular and widely spaced intervals, creating the illusion of a source that activates on a timescale of years rather than milliseconds. Another exotic idea involves a binary system where one object is a neutron star and the other is a massive, disruptive partner like a black hole or a dense debris disk. The bursts could be tied to the chaotic dynamics of this orbital dance, only occurring when the neutron star passes through a particularly dense clump of material in its companion's disk, triggering an eruption whose timing is governed by the complex physics of the accretion process. The existence of signals like the boomerang and other unclassified repeaters serves as a crucial reminder that our catalog of cosmic radio phenomena is still very much a first draft. For every neat category we create like FRB or pulsar, there are outliers that blur the lines, forcing us to acknowledge the breathtaking diversity of the universe's energetic engines. These mysterious repeaters are not failures of understanding. They are guideposts pointing toward entire classes of objects and physical processes we have not yet even begun to imagine, reminding us that the cosmos still holds profound secrets waiting to be decoded from the static. Yet for all our listening, for all our patient sifting through the cosmic noise for a message that might never come, a provocative question has begun to echo within the scientific community. What if we are being too quiet? What if the reason we haven't heard anything is because no one else is talking either? This line of thinking ignites the most controversial and spine-tingling chapter in the search for cosmic company, a practice known as active SETI, or messaging extraterrestrial intelligence. This is the moment we stop just listening and decide to start shouting into the void. The most famous of these deliberate shouts is known as the cosmic call message. In 1999, from the massive 70-meter dish of the Evpatoria Deep Space Center in Crimea, a team of scientists and enthusiasts beamed a carefully crafted digital message toward 4 carefully chosen sun-like stars. But this was no simple hello. The cosmic call message was a complex and layered communique designed to be a universal primer on humanity and our location. It began with a tutorial on basic mathematics and physics, using the universal constants of hydrogen as a starting point, establishing a common language of numbers and logic. It then provided a map, not of roads, but of time and space, pinpointing our location by referencing the unique rotational periods of 14 pulsars, the very same cosmic lighthouses we use to navigate, creating a triangulation point that would lead directly to our solar system. The message also included digitized photographs of human beings, images of our DNA double helix, and even personal greetings from people around the world. It was a bottle cast into the interstellar ocean, with our return address clearly stamped on the side. The rationale behind such an ambitious project was rooted in optimism and a fundamental shift in strategy. Proponents argued that if every civilization is only listening, then the galaxy must be silent. Someone has to make the first move, to take the courageous step that could break the cosmic ice. They pointed out that our own television and radio signals have been leaking into space for over a century, creating a fading bubble of evidence that we are here. A deliberate, powerful, and focused transmission, they argued, is far more efficient and likely to be noticed than our accidental cultural leakage. By sending a purposeful message rich with scientific information, we wouldn't just be saying, "We exist." We would be demonstrating that we are a curious, intelligent species capable of rational thought and eager to make contact. This act of cosmic outreach, however, sparked a firestorm of ethical debate that continues to rage today, a debate that cuts to the very core of our place in the universe. On one side stand the cautionaries, a group that includes towering scientific figures like the late Stephen Hawking. He famously drew a stark analogy, suggesting that broadcasting our location to an unknown and potentially ancient cosmos could be catastrophically naive, akin to the Native Americans first encountering Christopher Columbus, a meeting that did not end well for them. His warning was that an advanced civilization might not be benevolent. They could be nomadic resource harvesters, viewing a newly discovered planet like Earth not as a home for peers, but as a convenient supply depot. The dark forest hypothesis, a concept popularized in science fiction, suggests the universe might be a dangerous place where every civilization hides its location for fear of being hunted by predators. By shouting our presence, we might be revealing ourselves to the wrong listener. On the other side of this great divide are the advocates, who see this caution not as wisdom, but as a failure of nerve and a profound form of cosmic loneliness. They argue that any civilization advanced enough to travel between the stars would have certainly already detected our planet through other means, such as analyzing our atmosphere for biosignatures. Our fear, they suggest, is anthropomorphic. We are projecting our own human history of conquest and violence onto a canvas that might be painted with entirely different colors. The very fact that we have not been visited or obviously interfered with, they posit, could be evidence of a prevailing galactic ethic of non-interference or peace. Furthermore, the distances involved provide a natural safety buffer. Any response to a message like the cosmic call would take decades, if not centuries, to arrive, giving humanity ample time to mature and prepare. This is not a theoretical debate. It is a live one. Subsequent messages have been sent, including a 2008 transmission toward the exoplanet Gliese 581c and a 2017 beaming of a music festival toward a nearby star. Each new transmission reignites the argument, forcing us to confront a question for which there is no easy answer, a question that balances our innate curiosity against an unknowable risk. These deliberate transmissions represent the most profound signals of all, not those we are trying to decode, but those we are choosing to send. They are a testament to an audacious hope, a bet placed on the goodness of the cosmos, a decision to reach out a hand into the darkness, not knowing what, if anything, might eventually reach back and take it. But for all the mystery and false alarms of the past, we are standing on the brink of a new golden age of cosmic discovery, an era where our ability to listen to the universe is about to be transformed beyond recognition. This isn't merely an incremental step forward. It is a quantum leap powered by a new generation of telescopes so advanced they will turn the faint, frustrating whispers of today into clear, detailed conversations tomorrow. Leading this revolution is an international endeavor of staggering ambition, the Square Kilometer Array, or SKA. The name itself is a literal description of its collecting power. Instead of one large dish, the SKA will be a vast forest of antennas, with thousands of individual receptors spread across two continents, South Africa and Australia, working in perfect synchrony to create a virtual radio dish with a total collecting area of, you guessed it, 1 square kilometer. This immense sensitivity means the SKA won't just hear the universe's loudest screams. It will listen to its quietest murmurs, detecting signals so faint they are currently lost in the static, potentially uncovering entirely new classes of radio phenomena we haven't even dreamed of yet. What truly sets the SKA apart, beyond its sheer size, is its unprecedented field of view, and its astonishing data processing capability, while current telescopes like Parkes or Arecibo could scan an area of sky equivalent to holding a single grain of rice at arm's length. The SKA will be able to observe a section of sky larger than the full moon, and it will do this with microscopic precision. It will generate more data in a single day than the entire global internet traffic, requiring supercomputers of unparalleled power just to process the raw deluge of information. This combination means the SKA won't just find more signals, it will perform a continuous, all-sky census of the radio universe in real time, catching transient events that older technology would have inevitably missed. For fast radio bursts, this is the game changer. Instead of detecting a few hundred, the SKA is expected to find tens of thousands of them, providing a statistical sample so vast that patterns and subtypes we can't currently see will finally emerge from the noise, allowing us to finally categorize them and tie them definitively to their source objects, whether they are magnetars, neutron star collisions, or something even more exotic. Meanwhile, in the United States, another powerhouse is coming online with a similarly transformative mission. The Deep Synoptic Array, or DSA, in California is already demonstrating the future. This array of over 110-meter radio dishes is designed with one primary goal of pinpoint localization. While the SKA will find the signals, the DSA and its planned successor, the DSA 2000, will act as the universe's ultimate forensic investigators. Their incredibly high resolution will allow them to determine the exact galaxy, and even the exact region within a galaxy that a signal originated from, often within a single observation. This is the critical link that has been missing. Knowing a fast radio burst came from a distant dwarf galaxy is interesting, but knowing it came from a specific star-forming region next to a known supernova remnant within that galaxy is what provides the eureka moment. This precise localization will allow optical, infrared, and X-ray telescopes to swing into action immediately, training their eyes on the exact spot to see what else is happening there at the moment of the burst, finally providing the multi-wavelength context needed to solve the mystery of what powers these incredible explosions. And looking even further ahead, the next generation Very Large Array, or NGVLA, is being designed to peer into the cosmic dawn with breathtaking clarity. This proposed facility will have 10 times the sensitivity and resolution of the current VLA, allowing it to do more than just locate signals. It will be able to dissect them. Imagine not just knowing that a signal came from a magnetar, but being able to map the intricate structure of its magnetic field by analyzing the subtle polarization twists in the radio waves. The NGVLA could detect the faint, persistent radio glow from the debris of a shattered planet, or the gentle radio whisper of the magnetic field around a potentially habitable exoplanet. In the search for technosignatures, its power would be unparalleled. It could detect the equivalent of a common airport radar transmitter on a planet orbiting the nearest stars, and it could analyze any suspicious signal with such fine detail that it could distinguish between a natural astrophysical maser and a potential transmission with artificial modulation with a high degree of confidence, effectively ending the decades-long debate over signals like the signal by providing data so rich and unambiguous that their nature would become immediately clear. The promise of these observatories is not just more data, but a fundamental shift from mystery to understanding. They represent a collective global effort to move beyond merely cataloging anomalies and into an era of true cosmic diagnostics. With the SKA's vast census, the DSA's pinpoint forensic accuracy, and the NGVLA's exquisite analytical power, the enigmatic signals that have captivated and confounded us for decades will finally be forced to reveal their secrets. We are building the tools that will either finally hear the unmistakable whisper of another civilization, or will comprehensively map the natural, yet no less astonishing, symphony of a universe that is far more dynamic and violent than we ever imagined. The next great signal is out there, and for the first time, we are building ears capable of truly understanding what it has to say. From the legendary 72-second shout of the wow signal to the intricate, repeating cadence of fast radio burst 180916, and from the tantalizing false alarms of Gliese 581 to the profound, universe-spanning mystery of dark flow, we have journeyed through a cosmos that is anything but silent. We have encountered signals that vanish without a trace, signals that return with clockwork precision, and signals that are not signals at all, but the profound absence of them, like the enigmatic shadows cast by Tabby's star. Each one of these 25 mysteries, whether ultimately traced to a magnetar's starquake, a faulty microwave oven, or still lingering in the realm of the utterly unknown, shares a common, beautiful purpose. They are cosmic puzzles designed to stretch the very limits of human understanding. They force us to look beyond our comfortable assumptions and question everything we think we know about physics, about the universe, and about our own place within it. A mysterious blip on a chart compels us to build bigger telescopes. A signal that mimics an alien broadcast drives us to create more sophisticated filters. Even our greatest mistakes, like the Puritans or the LGM pulsar, are not failures. They are the essential friction that sharpens our tools and refines our questions, proving that the scientific process itself is a kind of conversation with the unknown, a continuous cycle of proposal, testing, and revision that pushes us ever closer to truth. The true value of this search is not in a final answer, but in the journey itself. It is in the collective effort of countless researchers staring at endless streams of data, in the global coordination of telescopes snapping into action at a moment's notice, and in the quiet hope that fuels both the careful, cautious listening of traditional SETI and the audacious, controversial shouts of METI. This endeavor reminds us that we are a species driven by an insatiable curiosity, forever reaching out from our tiny pale blue dot to ask the universe the most profound question of all: are we alone? So the next time you find yourself beneath a clear night sky, look up, let your gaze wander from star to star, from the familiar constellations to the deep black voids between them. Remember that within that immense, silent expanse, there are whispers we are only just learning to hear, whispers of collapsing stars, of whirling pulsars, of magnetic fields so powerful they twist the fabric of reality itself. And perhaps, just perhaps, one of those whispers is not a natural phenomenon at all, but a deliberate hello, a cosmic message in a bottle waiting for the moment we finally develop the wisdom and the technology to understand its language. The universe has been speaking for billions of years. Our great privilege and our greatest adventure is that we have only just begun to listen. Thank you for joining us on this incredible voyage across the cosmos, exploring the strange and awe-inspiring whispers that reach us from the deepest dark. If this journey through 25 of the universe's most baffling signals captivated your imagination, please show your support by giving this video a like. It truly helps us continue creating content that delves into the farthest frontiers of science and mystery. To make sure you never miss an adventure, be sure to subscribe to the channel and hit that notification bell. We have many more deep dives into space anomalies, cosmic paradoxes, and astronomical wonders coming your way. Now, we want to hear from you. After exploring everything from the legendary wow signal to the eerily precise rhythm of fast radio burst 180916, which of these 25 cosmic enigmas do you believe holds the most promise for being a true sign of extraterrestrial intelligence? Is it the one that perfectly matched the hydrogen line frequency, or the one that seems to repeat on a schedule we can almost predict? Share your thoughts and reasoning in the comments below. We read every single one and love sparking these conversations with such a curious and insightful community. If your appetite for cosmic mystery is now fully ignited, your journey doesn't have to end here. For a thought-provoking companion to this video, we highly recommend watching our deep dive into the Fermi paradox, which explores the haunting contradiction between the high probability of alien life and the stunning silence we seem to encounter. Or, if you're fascinated by the potential homes for these signals, check out our episode on the search for habitable exoplanets, where we investigate the worlds that might just host the civilizations we're so eager to find. Until our next exploration into the unknown, keep looking up and wondering about the incredible secrets hidden in the starlight.